Welcome back. So we have been looking at how to count using recurrences. So stepping back a little, so we have been looking at combinatorics, which is a branch of mathematics involving counting. And the typical question is how to count the cardinality of a set. And here we mostly talk about the case when the set is given implicitly and not explicitly. That is, the set is described in words and I want to know how many elements are there in the set. A typical example is how many elements of a universe satisfies a certain set of conditions. Or how many ways can I draw an element from the universe that satisfies a certain set of conditions. So here are some of the examples that we have already seen and how to tackle them. In fact, the big problem of counting is that all the problems are unique and one needs to apply a technique that fits it. Counting is in fact one of the most challenging subjects in mathematics, and big names in mathematics have also worked on this particular area. And we will be showing you some tricks and tools of how to count. So one of the things that we looked at is how to select k objects from n objects, and in that case we looked at whether the order in which we select the elements matter and whether we can select a same object multiple times. And for all the four cases, we came up with a solution which was a compact, nice, beautiful solution, like something like the n factorial by k factorial times n minus k factorial in this case. Now, similar problem was how to distribute n balls into k bins, and here also there are multiple cases to be looked at, namely whether the bins are distinguishable or whether the balls are distinguishable, or whether the ordering in the bins matter, or whether some of the bins can remain empty, and so on. Right? Now, and even in these cases also we came up with a certain set of answers to all the various cases, and they are mostly compact in the sense that we had some idea about what are these values are. And we used all these tricks to solve this set of problems. The final problem was this problem of how many 0-1 strings of length n are there that does not contain any consecutive 0. And the way in which we did this problem is that we started with the notation of Tn being the number of 0-1 string of length n that does not contain any consecutive 0. We proved that T1 equals to 2, T2 equals to 3. This we did by pure counting. And then we proved that Tn is equals to Tn minus 1 plus Tn minus 2. And this in fact gave us a procedure of computing Tn. Of course, we left it in the case that can we find a nice expression for Tn, and we will come back to this particular question later on in the next videos. But the main idea was that we basically converted the problem of counting into a recurrence relations. Or in other words, we converted it into a sequence of numbers so that we have a set of initial conditions and we can, any further term is defined as a function of the preceding terms. Right? So, here are the set of initial equations and here is the thing where it's a recurrence relation where the Tn is written as a function of tn minus 1 and tn minus 2. Now, recurrence relations have been extensively used in various subjects, and in fact they are one of the very strong ways of modeling problems, particularly counting problems. And solving recurrence relations is also a big part of this subject. Now in this video we will be looking at one more problem and see how we can model it using recurrence relation. The problem is called the Tower of Hanoi problem, and the main idea is that you have 3 poles and n disks of different size. So let me show you the picture. So something like this. You have 3 poles and you have these n disks here. These are the n disks 1, 2, 3, 4, and they are arranged in such a way that the smallest one is on top, the largest one is on the bottom, and so this one is bigger than this. So the one, so it is basically arranged in a decreasing form. And your goal is to somehow place all these things, all these n disks into this second one, into this one, into this. And what you can do, you can remove one at any point of time. You can remove one disk from here and put it anywhere. But you cannot put a bigger disk on a smaller disk. Okay? So let me go on it. Sorry. There are 3 posts and n disks of different size. Each disk has a hole through the center so that it fits on a post. At the start, all n disks are on the post 1. The disks are arranged by size, so the smallest is on the top and the largest is on the bottom. The goal is to end up with all the n disks in the same order on a different post. In a single move, one can move one disk from one post and place it to the another post, and at no point can one place a bigger disk over a smaller disk. Question is, how many steps will be taken to move n disks from post number 2 to any other post? So this is the typical picture of Tower of Hanoi. It's like the game that kids play, but you cannot place a bigger disk on top of a smaller disk on any of the posts. So question is that how many ways can you make the move? So for doing the counting, the typical way of doing it is, again, let Hn be the number of steps required to move n disks. Now if Hn is the number of steps required to move n disks, how many, so can we say something about this Hn? What about H1? So H1, since I cannot draw disks, so I will just draw them as numbers. Okay? So I have say 3 posts and I have this number 1. Now of course if I have to place this one in this next pole, I just need to pop this one out and proceed in the next one. So clearly H1 equals to 1, right? And this is the trivial thing. What about H2? H2 is interesting, right? So I have these 3 poles, say. In the first one I have 1 and then 2. How can I move this 1, 2 to the second pole? So of course the first thing that I have to do is I have to move this first thing and I move it to the first one. So I have made one move. Then I move the second one to the second place. So I make another move, 1. And in the third, I move the first one back to the second one, so which is one more move, and so. So good. So I make, so number of H2 is actually equals to 3. Let's do one more example. What about H3? So here I have 1, 2, and 3. I need to move this 1, 2, 3 to the next pole. Now I know how to move 1, 2 to the second pole. Maybe I can also move it to the second, third pole, right? So I can move 1 to here, 2 to here, then I move 1 from here to here. So I have till now made 3 moves, right? 3. Then I move this number 3 to this second one. I have made one more move, 4 moves, and now I move 1 to here, then I move 2 to here, and I move the 1 to here. So I have made, initially I had made 1, 2, 3, then I made one more move, then I made 2 more moves. So namely I have made 7 moves all total. So H3 is 7. Now like this, if I keep on continuing and say if I know H1 to Hn minus 1, can I compute Hn? And that is the question to be asked. So let's see first here. First of all, can I get an upper bound on Hn? If you remember what we did for the case of H3, let's see what was done. We first used Hn minus 1 step to move the top n minus 1 disks from the first pole to the third pole, right? That we can do because that's the definition of Hn minus 1. Then I moved the nth disk, the top bottommost disk, to the from the first pole to the second pole. And then again I moved the n minus 1 of them to on top of the second pole. So sorry, this is not third pole, this should be second pole. This is second pole, right? And this is also not the first pole, this is on the third pole. So I had it on the third pole, from third pole I moved it to the second pole. So in other words, total number of steps that I made was, of course, less than 2 times Hn minus 1 minus 1. So what we have is that the minimum number of steps required is less than or equal to 2 times Hn minus 1 minus 1. Now unfortunately this is just an upper bound. Can we get a lower bound? Or in other words, is it possible that this number Hn is strictly less than, sorry, I made a mistake, this is plus 1 of course. Can it be strictly less than Hn 2 times Hn minus 1 plus 1? And let's prove that it cannot be. So, okay, why it cannot be? So consider an algorithm that moves the n disks from the first pole to the second pole, right? Consider the time when the nth disk was moved. Of course, at some point of time, the last disk was moved from the first pole to the second pole. Now, before that move, it must have been the case that this top n-1 must have been moved from the first pole to the third pole. Why? Because when I moved the biggest disk from the first pole to the second pole, the first pole must have been empty other than that. And since the biggest disk cannot be placed on top of any of the other disks, so the second pole must also have been empty. Right? So the n-1 disk must have been sitting all of them in the third pole. Right? And of course, to complete the game, after I move the nth disk to the second pole, the n-1 disk must have been moved from the third disk to the second pole. Third pole to the second pole. So the number of steps that must have been made here is hn-1 and hn-1 and this one. So hn must have made hn-1 here, hn-1 here, and the 1 move here. So it is 2 times hn-1 plus 1. So in other words, what I get is that from the previous slide and this slide, that hn is actually equal to 2 times hn-1. So thus, for counting the number of steps required to move n disk, I have h1 equals to 1, I have h2 equals to 3, and hn equals to 2 times hn-1 plus 1. So as you can see here, we can clearly write down here now that okay, h3 equals to 2 times h2 plus 1, which is 7. H4 is 2 times h3 plus 1, which is 15. H5 is 31, and so on and so forth. So you can keep on doing this thing again and again and get some values. Question is that, is there a nice expression for hn? Or in other words, instead of just computing hn in brute force manner like this, is there a way of computing hn directly? So we have seen 2 examples of how to solve this counting problem using recurrence relation. Now there are many other recurrence relations that appears in real life. Of course, we have seen this is the one that we saw for the case of 0-1 to 0-1 string without any consecutive zeros. We also saw this one. Now if I change the initial conditions, for example in the first case I had changed the initial conditions to something like this, f1 equals to 1, f2 equals to 2, this is the famous Fibonacci sequence. Then we have things like, okay, b1 equals to 1 and bn equals to bn over 2 plus 1. This is something that arises from binary search. It's an algorithm. We have mn equals to 2 times mn by 2 plus n. This comes from what is called as merge sort algorithm. So various algorithms produce different types of such equations. And there are equations which are much more complicated like this, where Cn is a sum of square of them, and these are called Catalan numbers. Now, these are examples of recurrence relations. Recurrence relations, as you can see, is where the nth term is written as the function of the previous terms, as in this case. Now, there are techniques of solving these recurrence relations and getting a compact form for these recurrence relations. They are essential for not only counting but also for algorithms, for analysis of algorithms, for uh, various other subjects of math. In the next video, we will be looking at techniques of solving these recurrence relations. Thank you.